we're talking about our gas particles, they always exert a force on whatever container they're in. And so one of the things that will come out of this is something known as atmospheric pressure. And ultimately where our monitoring and determination of pressure as a unit came from. So if we take a look at the picture in the right-hand corner, what we've got here is a manometer, which I always find fun to say. In any case, we take a large container and we fill that container with some liquid in it, and then we take a tube with a closed end. We'd fill that tube with liquid.
I'm sorry, that's you. I was just showing her.
Wait a second. There's two of them.
Wait, you're apologizing because it's me? You're saying I'm interrupting myself?
Yes, you are.
It was you.
Strangely intertextual.
So the tube, then you put the open end in the liquid in the larger container, and what would you expect to happen to liquid in the tube? What would you expect to happen to the liquid in the tube? There's no gas. There's no gas.
Just to go down?
Okay, so the liquid in that tube should fall all the way out. There should be no liquid in that tube?
No, slowly it comes
There's gas
out.
inside the reservoir, eventually it'll have pressure where water can't fit in there anymore.
Right.
I would expect that when you turn it upside down.
I expect it to go down.
You would expect it to go all the way out?
No.
No. What would you expect it to do?
Oh, just stay there.
Stop
No,
where?
slowly.
When the pressure inside the reservoir matches the pressure outside.
Okay. There's a couple competing factors here. Why would the liquid come down?
Gravity.
Gravity. There's a gravity. There's a force of gravity causing the liquid to fall out of that tube downwards into the reservoir below. Right? There's also another competing force. That competing force is atmospheric pressure, also pushing down on the liquid in the reservoir. Well, if we have two things pushing down, shouldn't the liquid just entirely drain out?
No.
But aren't they both pushing down?
Well, the
No,
pressure outside of the
also
tube
on
is pushing the water back.
The atmospheric pressure is pushing down on the liquid on the outside, which is then putting pressure inwards towards the middle, which then means we get an upward force on the tube.
It's like a liquid pulley system.
Yeah, it's a liquid pulley system, sure. That keeps the liquid trapped up in the tube. So this observation, while we might have said, oh, it should totally fall out. Oh, it doesn't fall out. This is kind of bizarre and weird. I wonder what I could do with this. And so let's just say someone stared at this and was like, wow, this is magic. I wonder what's happening. And then they noticed that the liquid started to drop. And they go, oh, well, it is all going to slowly fall out. Okay, as the days went by, they noticed it continued to drop a little bit, and all of a sudden it went back up. Whoa! Why did it go back up? Magic. There's one option.
He's a witch.
Right? This comes back to... why'd you say he? It didn't have to be he.
Hey, witch is generalized, doesn't mean.
Yeah, quality.
Why would this liquid have the potential to both go down and up? The atmospheric, so gravity isn't going to change on us on an individual location, but atmospheric pressure could change. As the weather patterns change, the atmospheric pressure changes, which means the liquid in that tube can go up and down. So pressure was first described, usually in the meteorological sense, which I think I said that word correctly, in looking at weather patterns. Right? And it was that observation that then allowed us to say that this nothing that I see, or this nothing that I don't see, okay, does exert some force on the outside world, okay, on the world that I'm in. That is now my atmospheric pressure. Gases do exist. I may not be able to see them, but they are actually exerting a force on my world. Okay? And that's our atmospheric pressure, okay? Which is kind of a neat observation to go through and make. Okay? The next part behind this is that, well, what liquid did we... Yeah, not quite that. We could then quantify how tall that tube was, or how tall the liquid was inside that tube. Right? So that's a distance or length. So we could measure that in units of centimeters, inches, meters, millimeters. Right? Of what? Of whatever the liquid was in the tube. Well, in this case, we've got a hint. What is the liquid in the tube? Mercury. So we could reference atmospheric pressure now as the measure of length of that tube of mercury. And as long as we use the same tube in different areas, or the same thickness tube, the same diameter of that hole, everything would work out, and we could now compare pressures in different locations around the world. Okay? So kind of a neat little observation. Why are we using mercury?
It's a liquid at room temperature.
So there we go. Big observation. It's a liquid. That's why we're using mercury. It needs to be a liquid, because if it's a solid, is it going to move?
No.
No. Okay. Silly goose. Yeah, thank you. Okay. Why not use water? Isn't water a liquid at room temperature? Okay. When we're looking at this process, we're picking a liquid that doesn't turn into the gas phase easily. If that was water, what happens? Okay. What's constantly happening to the water that's exposed to the atmosphere? It evaporates, meaning it turns into a gas. Once it becomes a gas, well then the natural flow of air movement removes the gas from the surface of that, and now the liquid says, well, I can become a gas again. And so it constantly cycles across to make more gas particles, even though we're not at the boiling point. The issue is now all of that liquid is now a gas, and I now have no pressure pushing back up against. And so everything kind of drains out of that. Mercury, on the other hand, does not transition easily from the liquid to gas phase. Okay? This isn't a boiling point because we aren't boiling the water. Okay? There's another principle that's coming in here. Mercury just happens to be less susceptible to becoming a gas. And what is that principle? As a hint, we're talking about it being a gas, so how might we monitor it? How do we monitor our gases?
Atmospheric pressure.
By using pressure, not atmospheric pressure, because the atmospheric pressure is what's already there. Okay? So pressure is a good way to represent this. But I'm not looking at the pressure of the atmosphere. I'm looking at the pressure of what? Pressure being generated from what species? The liquid that was in there, okay, or mercury. Okay, so I'm looking at the liquid transitioning into the pressure system. I could call it liquid pressure. Doesn't quite make any sense, but that's where we get the term vapor pressure. Okay? We're talking about, it sounds a whole lot nicer, doesn't it? We're talking about what the vapor pressure is, the amount of gas that naturally becomes evolved from a liquid. Okay? That is our vapor pressure. Different substances have different vapor pressures, just like they have different boiling points or melting points. And there's a variety of things that contribute to them. But what we're looking at with our vapor pressure is the ability to transition into that gas phase. When we look at mercury, it does not transition into the gas phase a lot, which is why it's great for our manometers, because it doesn't disappear. If we use, say, water, that becomes problematic, because that then evaporates, and we now don't have anything to measure with. Okay? So, other things that kind of track, vapor pressure will increase as the temperature increases. Why might that be the case?
Because particles are expanding.
Our particles are starting to move more. Okay? We're starting to actually get closer and closer to the boiling point. Well, what happens at the boiling point? A full transition from a liquid to a gas. So the hotter we become, the more likely our vapor pressure is going to increase. We're going to start to see more of the gas particles floating around. Okay? What if we tried to do the reverse of this? I want to now get gases to dissolve into my liquid.
You get it really cold.
Okay, why do I want to get it really, really cold?
To reduce the phase change from gas back to liquid.
Okay. To dissolve the gas into the liquid, what are we trying to do? And I agree with this, Ryland. We're taking the gas and we're making it a liquid. Okay. Well, how do I make a gas a liquid when I look at temperature?
You do the opposite of what you did to make it.
I could do the opposite of what I did to go from a liquid to a gas. And what did I do to make it go from a liquid to a gas? Increase temperature. So to reverse it, I should Decreased temperature. So I see more gases dissolved at lower temperatures. Everybody agree? Right. We talked about solubility before, right? Dissolving solubility. Remember? Do you remember talking about solubility of substances?
Yes.
Yeah, the solubility of, say, solids. How do I get a solid to dissolve?
Heat it up.
I heated it up.
Increase temperature.
Anybody seeing an issue here?
Yeah, this one's decreasing.
This is decreasing, and yet when we previously talked about solubility, it's increasing. So what does that mean? That means chemistry is full of exceptions. We should never memorize a rule. No.
Gas and solids are different.
Look at what's happening in that process. As Ryland accurately pointed out, for dissolving the gas, we're taking a gas and going to a liquid. To do that, I need to decrease the temperature because I'm trying to cause the phase change the opposite direction. Why does it appear to be counter to that when looking at the solid? Well, what am I trying to do with the solid? I'm trying to take my solid and turn it into a liquid. How do I do that phase transition? By increasing the temperature. So it's not an opposite system. You're dealing with a different substance. When you change that substance, we have to change our frame of reference on what we're looking at within those. Kind of make sense?
Yes.
Okay. Gases are a little bit different than solids, okay? Because there's another system that we can use to measure our gases. What is that other system? It's at the top of the page. Let's remove the first word. Pressure. We have pressure to evaluate our gases. Okay? So how could I change the pressure to get my gas to turn into a liquid? Okay, I could increase the pressure. Okay, because literally what I'm trying to do is take those gas particles that are now just bouncing everywhere and saying, you can't bounce everywhere, you must bounce in this tiny little space.
They're kids.
Okay? I'm trying to control them. The only way I can corral them is by forcing them in. The force that we use to describe our gases is pressure. You can stop making those references. We don't need that. So we can increase our pressure or decrease the temperature. When we looked at the solid to liquid, did we talk about pressure?
No.
Why not?
Because it's not gas.
Not dealing with gas.
Okay. It has to do with the different phase. The gases are dictated by pressure. Solids and liquids don't dictate pressure or don't have a pressure component behind them. Okay? Why do they not have a pressure component behind them? That actually gets into one of the later or the next kind of variable that contributes to our gases, which is volume. We'll get at in a little bit.
Yeah, you said liquids don't contribute pressure. You know when you go in the ocean, like for scuba diving or something, you go way down, the pressure gets
True.
extremely-
That's a good point. You are getting an increased pressure there because of the amount. When we're going back to our solids to liquids, the amount change there isn't drastic enough to see much of a pressure differential. So that's a good point. So if you go far enough, you're now getting a gravitational effect of everything above you stacking.
But in certain situations with solids, if you apply heat and pressure, it could turn into a harder solid. Or is that like a diamond? Like say you take.
We can do pressure to adjust some things with our liquids and our solids. Okay? But for the most part, it's a small effect. Why do we see a small effect with pressure with our solids and liquids?
Not as much room for.
Look at the physical phases for those. A gas has particles all over the place. A liquid has more particles and less space, which means as I put more pressure on it, what's going to happen? Well, the particles are like, I'm already right next to each other. Push me. What are you going to do? Solid, what happens?
They're already really close to each other.
They're now so insanely close to each other that there isn't a large pressure differential. Yes, different substances, both our liquids and solids, under higher or lower pressures can change their crystal structure in very minute fashions that turn into large effects in what we can observe. This is why when we look at graphite in your pencil versus diamonds, both of those are carbon, and yet we see the importance of those two species as very drastically different, because the diamond was put under extremely high temperature and pressure to help force and change how those atoms were aligned. Okay? So there is a spatial differential within those. It isn't quite as simple as just saying, well, they're all right next to each other. Kind of, sort of. Way to dig so far deep into that we didn't need to. But that's cool. I like that.
Is there an actual chemical, this is just pure curiosity now, is there an
Go
actual
for it.
chemical change when carbon changes into a diamond? Like,
You start running the thresholds of what is chemical versus physical on those lines. So you probably don't want the answer to that. is where I will go with that. Because that's going to start to go into what is salts dissolving in water. We already hit an example that crosses the boundaries between chemical and physical, and that was hard enough to deal with. If we bring in more, that can make it even more difficult. So let's hold off on that. If you want to talk about that after class, we can. If anybody else is super curious, you can talk after class too, but it's kind of beyond the realm of what we need for the class. Okay? So, units of pressure. We talked about some, because we're looking at the height of a mercury tube. So we could have a distance. Okay, we could do inches of mercury, Hg. Oh, that's right. That was our symbol for mercury, right? Hg. Just checking. Centimeters of mercury, millimeters of mercury. Okay, all of those are based off of that initial observation of the height of mercury in the tube. Okay, and they happen to be 76, 760, depending on the unit system you were in. Right? But then if we go through and take a look at some of these others, we get 760 torr. Torr, that makes perfect sense. Torr coming from a guy's name. ATM. Atmospheres. Right? PSI. Pounds per square inch. KPA. Kilopascals. What is a Pascal? A pressure unit named after a scientist. Why do we have so many different unit systems for pressure?
each one's related to the type of substance you're dealing with? No?
Okay. Some of it comes back to the different areas that you're looking at. No, you're right. Okay. Pounds per square inch. Where have you seen pounds per square inch?
Gases.
In tires, right? When you're talking about the gases put into a tire. Because you don't want to put so much force, that weight, pounds, per an individual square inch, because what happens when you exceed that pound per square inch? The tire pops or blows up. That becomes a bit problematic. So we're trying to come up with a way that allows us to relate that information, or encode that information, if you will, into a way that makes sense for our everyday populace. Okay? Why use centimeters of mercury, or millimeters of mercury, or inches of mercury? It had to do with the tool that we used to measure it. Okay? Couldn't we have used that same tool to measure our pounds per square inch? Yes, we absolutely could have, and that would have generated a different number, and we'd be used to that number system. Why do we have so many different ones? This observation on gases, while it seems kind of not super likely to make, was one that was made in multiple cases. You could walk down and be like, why do I feel this weird thing blowing against me, but I don't see anything? What is that? Oh, it's wind. Well, what is wind? How do I measure it? Okay. Or, Josh, that's... Don't finish it. Yeah, we'll finish that. Air is now moving around us, so we'll come up with different ways to then monitor or observe that and quantify it. Right? The issue is then that because so many people made these observations, each of those then tribes, if you will, got together and said, oh, we all made a similar observation on this one thing. Let's all call it this. Well, why should I call it what you call it? I'm going to call it this. You should call it this. And then they fought and decided that it wasn't worth fighting anymore, that they just agreed to disagree and make your lives hell because you now have to deal with all those conversions. Not chemistry. Don't blame the chemists. This is science in general. Okay? This is engineers. This is physicists. This is chemists. This is biologists. Okay? This is all of these people getting together and just eventually deciding that it doesn't make sense to all agree on a single system as long as we know how to convert between those systems. Right? Which, yes, makes that a little bit more problematic for you because you have to do those conversions. But it's not that problematic for you because you spent the last 5 weeks studying dimensional analysis and you're now rock stars with dimensional analysis, and those conversions are next to nothing as far as difficulty for you, theoretically. Okay? So how many of those conversions should you memorize? Or let's take a step back. When we looked at our conversions, we said they were equalities, right? Typically, when you look at an equality, what do you see in it? An equal, yes, an equal sign. That's what we see when we talk about equalities. Anybody see an equal sign anywhere in this?
No.
No. What are they actually showing? They're saying 1 atmosphere is 29.9 inches of mercury, is 76 centimeters of mercury, is 760 millimeters of mercury. So by listing it out in this table, they've actually given us tons of conversion factors. Okay? They're telling us that 76 centimeters of mercury is 14.7 psi. Okay? That is now in that information because they're all set to be equal to each other in this table. That's the whole point of it. So we now have the ability to convert between any of those within this. Okay? Why might we not like that conversion factor? These are all gases. There's no liquids. When we talk about molar mass, give me a molar mass of carbon. 12 is not a molar mass. 12 is the number of eggs in my thing. A dozen. I was trying not to say a dozen. That I ate for breakfast this morning. I did not eat 12 eggs. What is 12?
It's atomic weight.
Okay, atomic weight. What is the unit on atomic weight? AMU. I didn't ask for AMU, I asked for molar mass. I want the molar mass for carbon.
Molar mass for carbon is 12.01.
12.01 is
Grams,
not...
sorry.
12.01 grams is better, but not the molar mass. You're starting to fish at something. What do you got? 12.01 grams of carbon is equal to 1 mole of carbon. The molar mass relates the grams and moles. So it was a number of grams equal to 1 mole. What was Avogadro's number?
6.022 times 10 to the 23rd.
No. What was Avogadro's number?
Okay. Oh, 1 mole.
1 mole equals 6.022 times 10 to the 23rd units. Okay? In our unit system, we had a number, we had a unit, and then we had an equals 1 of something else. It was usually a nice, easy transfer, miles per hour. I'm going 65 miles per hour. That's 65 miles equals 1 hour. There's a 1 in it. Why might we not like some of these conversions? Is 14.7 1? No. Is 76 1? No. So we're relating two conversion factors, different units, and the numbers don't come out quite as nicely. Yes, as an interesting observation, some of those include decimal points as well. Okay? So, how many of those should you go through to memorize? Absolutely none of them.
Yes.
Okay?
You're going to give it to us like a table on the test?
I will not give you any of these.
Couldn't they ask you like
I will not give you any of these. Why are you not supposed to memorize them then if I'm not going to give them to you?
Because it's not going to be on our exam.
You're not expected to be able to convert between these on the exam. You're expected to be able to convert between these unit systems in the homework, so be aware of that.
couldn't they ask questions like
We could always ask lots of questions there, but we're just going to let that go. Okay, so variables that affect our gas pressure, okay, or that we need to monitor for a gas. We already have addressed one of those. What's something that could affect our affect our gases? Pressure. Temperature. What else could affect our gases? The substance. What do you mean? Well, you asked the question.
I'm saying, I mean, like, it's kind of what we were talking about in
in chemistry?
in English, just like how like we're us being like the writer and everything, we still like impact whatever's going on. So I'm saying like, okay, the substance clearly impacts what's going on as well.
Okay, so then what I'm now asking is how does it impact? So we're talking about the pressure. How does a different substance affect the pressure?
I said the solubility.
No. So let's pick two substances. Let's pick hydrogen and let's pick xenon. I'm going to pick xenon. What is the xenon is Xe.
Yeah, one of them could be like more dense than the other
The electronegativity of it.
The weight?
When does location on the
Like,
if you're at the top
We'll
of the mountain,
deal with that later too. Let's get back to this. Does the substance affect? What is the difference? And because we're starting to hear something about electronegativity, let's just change it to helium then. Helium versus xenon. So now electronegativity out the door, doesn't work.
Okay, and the atomic mass.
The atomic mass. Okay, is atomic mass affecting pressure?
I mean, we don't know. Unless we were really
Okay.
exploring.
No. Why does the atomic mass not affect the pressure?
the mass of something doesn't change.
This has to do with what our gases are and how we define our ideal gases. We made some very important assumptions when we started talking about gases. What was the very first assumption we made? About gases, yes. So one of the assumptions was they all move in random directions.
We can't
Okay.
find the volume.
Say that again.
We can't find the volume, but they don't
So
have
wait,
a volume.
Our first assumption is that our gas particles do not have a volume.
yeah.
So when I look at helium versus xenon, yes, they may have different masses and they may have different electrons, but that does not change the size of the particles. The particles are now going to have the exact same effect on their environment. The type of particle is actually not a contributor to our pressure. So that was a no. Nothing else affects pressure, right? How about volume? Okay, if I had a balloon and I started to shrink that or try and squeeze that balloon to shrink the volume of the balloon, what eventually happens? It pops. Why? The pressure changed. Does that affect the pressure? Yeah, because I'm changing the volume, it changed the pressure. So volume contributes. What else can contribute?
I feel like you're changing the pressure, not the volume.
I'm changing the volume by shrinking the volume of the container, which then requires that the pressure also change. How about the number of particles that are present? If I take a balloon and I blow into it, what am I putting into the balloon? I'm putting in more particles. Does that change the pressure? If I continue to blow into that balloon, eventually what happens? It pops because the pressure has overwhelmed the size of the container. So we end up getting these four symbols, and yes, as Rylan is suggesting, they are all interrelated. As we add more moles, what happens to the pressure? The pressure goes up. As I decrease the volume, what happened to the pressure? The pressure went up. What happens as I increase the temperature? The pressure goes up. What happens if I decrease the pressure? The pressure goes down. Thank you. That is exactly what I was fishing for, so I appreciate that. Right? So we have these relationships. All of those went back to pressure, but could I do the same thing for volume? Okay? What happens if I increase the number of particles? What's going to happen to the volume? It's going to get bigger. Okay? What happens if I decrease the volume? The volume gets smaller. Good. What happens if I increase the temperature? What happens to the volume? That one's a little bit harder. Anybody seen a hot air balloon? Yeah. Have you ever seen a hot air balloon deflated? Okay. How do they get it inflated? How do they get it to show its full volume? They add heat. Not, you just like, yeah. Again, there's no way I can nicely say that, so we're just going to let that go. Pressure. What happens if I decrease the pressure? What happens to the
You're
volume?
asking if you decrease pressure.
If I decrease the pressure, what happens to the volume?
Stays.
Okay, this is hard. We've got a lot of different things going on. Okay. What happens if, let's flip it on its head. Let's look at what happens if we decreased the volume. What would happen to the pressure? Okay. If I take that balloon and I now try to shrink the volume and shrink it down, what happens to the balloon? The pressure goes up. So what happens if the pressure goes down? The volume had to go up. Okay? So we can start to generate relationships between all of these things. And several important figures in science have gone, and ultimately physicists, went through and noticed this and started to say, oh, well, these relationships are tied through a constant. Okay? Well, another scientist went through and said, well, these relationships are tied through a constant. So, well, but when I look at these ones, these are related through a constant. So eventually someone smart enough said, stop dicking around with all the individual ones and put them all together into one big thing. That one big thing is the ideal gas law. They noted that when you relate pressure, volume, the number of particles, and temperature in the fashion shown below, that you will generate R. Okay. Why did they pick R? Because M was taken. Right? We picked capital R to represent this constant, and they noted that it always came out to be the numerical value given above. What is R? Do not tell me that number. What is R, but do not tell me 0.0821? Fair answer. Maybe that's what I was fishing for. Oh, no, that wasn't what I was fishing for. I remember. I don't want constant. Give me something else. What is R?
What?
It's the volume, the pressure, the moles. Yeah. Keep going. What is R? Right, let's try it another way. What is speed? Don't tell me drugs. Distance over time. What does speed allow me to do? Right? Measure how fast. If I give you the speed in some time, what can you do?
Tell the distance.
You can tell the distance. What does speed allow you to do?
Tell you the time and distance.
Convert time and distance. Right? Because I have a system that relates those two units. What is R? It relates atoms, liters, moles, and Kelvin in a conversion factor. R is merely a conversion factor, allowing you to relate all of those units simultaneously. Okay? Speed is a conversion factor that only relates 2 units. Molar mass is a conversion factor that allows you to relate grams and moles. R is a conversion factor that allows you to relate simultaneously atmospheres, liters, moles, and Kelvin. Okay? That is all R is a conversion factor. Okay? It's a neat one because it's constant. It always is true. Okay? It's also a big nasty one because it relates 4 units at the same time. Okay? So this would be the one case where I would recommend that you don't deal with it as dimensional analysis and you instead deal with your gas solvings based off of the equation. Okay? R equals PV over NT. How many people like fractions? One person in the class likes fractions. The rest of you apparently don't. Okay? So how can we rearrange this equation so that we can memorize it without a fraction? As soon as you say divided by, you have a fraction. PV equals nRT is the standard description. You'll typically hear chemists talk about it as Pivnert. Right? It's a way to memorize as opposed to Turnvip. That's actually not too bad. But in any case, Pivnert gets us the system that allows us to now convert or relate pressure, volume, moles, and temperature. So when we go back and consider all of these awesome relationships, Boyle, Gay-Lussac, Avogadro's, Charles, all of those are looking at individual relationships between just two of those things that affect gas pressure. Okay? We could go through and memorize each of those relationships. And there's a certain thing to be said for the amount of work they put in behind it to come up with those relationships, and we should honor that. So we can take a moment. They are now honored. Deal with Pivnert. Okay? Pivnert is going to be our best relationship. With that, we now have the power to convert and deal with all of their independent laws jammed together in one big thing. Okay? The assumptions that they made when they went through and found their observations is the variables that they weren't studying, they assumed to be constant. Okay? So they disappeared from the ideal gas law. Okay? They just became irrelevant. So the power behind this is that I can now predict what would happen in secondary conditions. Okay? Because I can take the conditions of my gas, or take my gas at conditions A, and if I change those conditions, I can predict what would happen to the unknown variables. Okay? Through the ideal gas law, because I know they have to be constant. Okay? So let's test that. The container, or the volume of a container, is doubled. Assume the temperature and the moles are not changed. What happens to the pressure? Okay. Some people can propagate through this. Okay. Some people can go ahead and propagate this in your head. Okay. And I would make the argument we, again, don't want to deal with the propagation through our head. We want the organizational system that allows us to go through and solve if for some reason temperature and moles were also changed. Right? So how do we go through and do that? Okay, well, what we're concerned about, let's just clean all that up, is looking at all the information that's given. Okay, number one, this is a gas. So what does that mean? It's stupid. Thank you.
Are you saying that the gas, the volume of what's inside the container was doubled, or
The volume of the container was doubled. Okay. So we have an idea here. We heard that the pressure would go down. Okay. We came up with that relationship earlier. Unfortunately, that's not a full answer. The full answer wants a numerical relationship. So you've got an idea that it should go down. You can eliminate answers that say that it goes up. So that's useful. Okay. But I want a numerical relationship. Okay. So how can I do that? Well, because I know it's a gas, I need to be looking at pressure, volume, moles, and temperature. Okay?
Did you say moles or moles?
Moles.
Why is it an N and not an M?
That's the number.
Because it's N for the number of particles.
Oh, okay.
And why would it not be M?
Probably taken by like meters or something.
M is already taken by meters. Okay, so I would go through and say we have two conditions. We have conditions A and we have conditions B. Okay, or initial and final. Okay. Temperature and moles are not changed. What is the temperature then? Constant, but I want something to put in there. I want to put something in my category right here and right here. I could pick really anything I wanted. Okay. I would make the argument that I should pick T. I don't really care what it is. It's T. What is the intersect of T and B? What is the next one? It is also T. How do I know it's also T? Because it says it didn't change. What is my value for moles? N. And? N. Awesome. Okay. What is my value for pressure A?
The pressure divided by time, I mean temperature.
Am I given a numerical value for it?
No.
No. So I'm just going to, whoops, I said pressure, right? So I'm just going to say it's pressure A. I don't know what it is, but it's pressure A. Okay? What is pressure B? pressure B. And you're like, oh my God, this is not looking very happy. Okay, wait for it. How about volume? What is volume A?
Double, so double VA.
Right.
2VB.
Okay, so I'm hearing that we're going to solve, well, we'll just run with it and see. You're telling me that pressure A is what?
2.
I'm hearing a VA, so we'll run with that. What is pressure B? 2VA. It's not VB. We're saying that we doubled the size of the container. So the volume for B is now just twice the size that it was originally. It's 2 times VA. Yeah?
Yep.
Okay. That's an awful lot of variables to come up with an actual number out of this. Okay? Remember the system we need to be dealing with? We know R is always a constant. So we can start to plug these things in. PA times VA over N and T. Why not NA?
Because it's changed.
It didn't change, so I don't have to add that extra layer of information. What do I know this is equal to? Yes, I know it's equal to R. What else do I know it's equal to? I know it's equal to PB and 2VA. Where'd you get that from? That's the volume for B. All I'm doing is making the substitution in. Over NT. What happens?
Common denominators.
Those common denominators cancel. I would end up with PA times VA equals PB times 2VA. Now what can I do?
Divide by
Divide
VA.
2. Oh, just divide VA because it's just VA.
Okay, divide just by VA. Okay.
Yeah.
What do I notice?
They cancel out.
I get PA equals
PBVA.
1/2 PB. Whoops, I don't know why I did that. Oh, I was dividing by 2. You guys switched it on
Yeah,
me.
we switched it because we knew that was going to happen.
2 times PB. Okay. What does that suggest happened to the pressure? Didn't you say it was not supposed to double?
Yes, it did say that. So what's happening?
So what happened? This is where being careful with your frame of reference comes into play. Okay. What are we solving for?
Oh, pressure. Pressure.
Which pressure? We're solving for PB. What did our equation solve for?
Oh, so
Did we solve for PB?
So you got to divide by 2.
No, we solved for PA.
Yeah.
That's why somebody wanted to divide both sides by 2. Because if we divide both sides by 2, what happens? I love the nonlinear aspect of this. I get 1/2 PA equals PB. My new pressure is now 1/2 the size of the starting pressure. Okay. Being careful with your frame of reference can help you out in nailing that down. This is why it's very important, as Ryland had jumped out and said, that the what are we looking at? Pressure. The pressure should have gone down. So that when you run the calculation, you can now say, ooh, double. It shouldn't have doubled. What happened? Oh, I changed my frame of reference. I'm not solving for the thing I was set out to solve for. Right? So it is useful to have an idea of those relationships already nailed down in your head so that you have a good guess. Once you have that guess, you can then go through and use the mathematics to back you up.
So, I mean, dividing by VA and everything else was correct. We just didn't go far enough. We still needed to divide by 2. We got
It comes down to what you're trying to solve for. Yep, and that was the issue, is that you guys didn't solve for the correct part. We're trying to see the relationship back to our starting condition. Okay? that can be made a little bit easier. Instead of solving for A and B, we could solve for I and F. Why I and F? I'm in the initial, sorry, the upper right.
Initial and final.
If I solve for an initial and final, that can help me keep clear track of what I'm solving for or what I want to keep. Make sense? Okay. So that's the power of our ideal gas law. It's kind of neat. Okay. So we'll look at a new question here. How many moles of neon gas occupy 2.34 liters at STP? Okay. Go through and solve this as best you can. Okay. If you think you've got it solved, try and solve it a second way. There are two ways to solve this question. See what you can come up with. If you got questions, raise your hand. I'll come to you. We're going to go through and set this up for two ways. Okay? And this ties back to the lecture yesterday. So first off, we'll go through and try and crunch it through the way we've been talking about dimensional analysis. Because if we reference earlier in this video, you go back and rewind back, I say for gases, we can take a step away from dimensional analysis and we can just memorize an equation and use that equation. Okay, I said you can do that. Okay? But for the sake of this, let's go through and just see what happens with dimensional analysis. What am I solving for? What is step one?
Moles of neon gas.
Moles of neon, I'm going to write gas. What am I given? 2.34 liters.
STP.
What element is STP?
Standard temperature pressure.
What element? Sulfur.
Sulfur, and T is not even on the periodic table. What the hell is STP? That's not a thing. I measured 2.34 liters of standardized temperature and pressure.
Well, at standard.
Oh, I measured that at. What did I measure? Liters of something. I agree. What was that liters of? Neon gas. Come on. So I would then take a look at this and say liters, moles, right? That should be my conversion. I ideally want that system. For those of you vigorously erasing, you might have actually been correct, so you might be careful with that. All right? And now we run into a dilemma. I'd have to know that conversion factor. For those of you that you do know it, keep your mouth shut. For those of you that don't know it, do you know this conversion factor?
If they don't know it.
Exactly right. For those of you that don't know it, do you know this? No, because you don't know it. Okay, so we don't know that conversion factor, so now we're kind of dead in the water until we realize that Mike said, because it's a gas, I don't have to do dimensional analysis. And I hate dimensional analysis, so I'm not going to do dimensional analysis. I'm going to remember that I have PV equals nRT, where pressure is what? Am I given the pressure in this question? I'm told 1 atmosphere. How did I know it was on 1 atmosphere? Because it says STP, which stood for standard temperature and pressure, and for the sake of chemistry, standard pressure is 1 atmosphere. So I'm given that information. Am I told what the volume is?
Yes.
What is the volume?
2.34 liters.
What is not the volume? 2.34 was the volume.
Liter.
Sorry, I thought I might have gotten 1 snicker out of that. That might be a grenade joke. We'll see what happens later.
I don't get it.
N, it's okay. Nobody else did either.
I was writing vigorously.
N, what is N?
We're solving for.
What we're solving for, I don't know what that is, so we can call that X moles. Okay? What was the last one? T.
T. 0 Celsius.
T would be 0 degrees Celsius. So I could now go through and try and jam these things in. Pivnert, I can change around to solve for N. N equals, yeah, it's a horrible standard. This was a discussion we had earlier. You should go back and watch those videos. PV over RT. Okay? And we can start to substitute these things in. N will be equal 1 atmosphere times our volume, 2.34 liters. And actually, I'm going to pause here for a second. And by pause, I'm just going to be like, I don't, something about that V just bothers me. It's a good thing she walked out. It'll be extra funny if she watches the video. Sorry, V. I apologize. R. What was R? 0.0821 atmospheres times liters over moles times kelvins. And you're like, ah, that's an ugly unit. Yeah, it is. I agree. Temperature. Okay. It did not say Kelvin, right? We said 0 degrees Celsius. Why is 0 degrees Celsius going to be a problem in our calculation? I'd get 0 in the denominator, and that's going to look all sorts of weird. That means I have 0 particles. God, I wish scientists invented a better temperature unit that would prevent this from happening, that they included in R to allow me to know that 0 degrees Celsius was a horrible idea. Oh, they did. It's called Kelvin. I need to convert my degrees Celsius into Kelvin. How do I convert to Kelvin? You just add 273. So I don't use degrees Celsius. I would use 273 Kelvin. Okay. We still have to include the volume. Okay. So that has to get thrown in here. I'm just going to throw it in a slightly different color here, though, at the end. So we said the volume was what, 2.34. Sorry, we're running out of space there at the end. Liters. Right? If we go through and check our work, what happens? Atmospheres cancel, liters cancel, kelvins cancel. Okay, I'd go through, let's ignore the numbers for the moment. We have for our units 1 over moles. We go, oof, that's not moles. Let's make mole 2. What is 1 divided by 1 over 2?
2.
Oh, it's 2. What is 1 over moles? Neat. Algebra is fun. And we get moles. So I could enter it into the calculator. 1 times 2.34 divided by 0.0821 times 273, and I'd get a magic number of... No one did it?
0.104 moles.
0.104? Okay. Do I get a second on that?
That's what I got from the way I did.
Oh, okay. That's cool. So the standalone class can't do math then.
That's what I got. The other one, like the
Okay.
top one.
So, for those of you that now, so we now have an answer. We went through, we looked at it as the full-on gas system. We had a formula. We just plugged and chugged through the formula. We didn't have to think about it. We just had to make sure our units matched, and boof, we have an answer. Cool. Okay. Could we have done this with dimensional analysis? So this goes back up to that top solve. We had this relationship between moles and liters. Okay. I did hear a suggestion, oh, moles and liters is molarity. That is true. Moles and liters is molarity for not solids or liquids. Not absolutely not gases. Solutions. Aqueous solutions. Is this an aqueous solution? No, this is a gas, so I can't use molarity. Okay? But we had that kind of annoying system that I talked about and complained about a whole lot, but apparently no one decided, well, you did actually, because you remembered it. You remembered that that conversion factor is 1 mole happens to be 22.4. When is that conversion factor valid?
At STP.
When it's a gas and it's at STP. Am I a gas?
Yeah.
Am I at STP?
Yes.
Yes, both conditions are true. I can use that conversion factor. I go through and do that math using different numbers, right? 2.34 showed up, so that's kind of the same. But 22.4 is not those other numbers. What do I get as an answer? Give me that different number.
0.10.
think that's the same number.
It's
106.
the same room.
Oh, it's the same.
Yeah.
But 22.4 is not 1 divided by 0.0821 times 273. Right? There's no way.
It sounds sarcastic.
It's just
It does sound kind of sarcastic, doesn't it?
It is sarcastic.
It's because it is sarcastic. Guess what the answer is? 1 divided by 0.0821 times 273 is 1 over 22.4. They're one and the same. The relationship that they told you to memorize comes out of the ideal gas law. At STP, meaning when it's 1 atmosphere and 273 Kelvin. That's why that equation is valid, because of the ideal gas law.
Thank you.
Right? Why is that conversion stupid to memorize? As Michael pointed out, 0 degrees Celsius, how is that standard? That's frickin' cold. He didn't say that, but close enough. Right? Verbatim? Oh, okay, even better. Okay. That doesn't make sense. I would never do an experiment at 0 degrees Celsius. You're probably right. You never would. Okay? But that makes the math of converting degrees Celsius to Kelvin a lot easier, so I can just blanket make that statement. And now, oh, it's so much easier. And now we tell you to memorize that. Okay? The origin behind that is PIVNERT. That's where it's coming from. When does that I already forgot it, 1 mole equals 22.4 liters valid? At STP and gases. Okay? You will likely work with gases when you solve questions. In the real world, will you ever be at STP? Probably never. So is that conversion useful? No. The only time that is useful is in this class, when working with gases, when at STP. When is PIVNERT valid?
Always.
Always. That's the power of PIVNERT. Did you see a typo or you want to write something?
No, I just want-
Oh yeah, there we go.
So, if we're tying this back, PIVNERT links to the process or the algorithm for solving these types of problems. It's always applicable. The ideal gas law only matches one specific content, or the STP only matches one specific scenario, and that links to the content we talked about.
Kind of makes sense.
Should walk out.
I should have put it.
You even slam the door. You can't slam these doors. Right? Kind of makes sense?
Yeah.
Cool. Don't tell her that. Dalton's Law of Partial Pressures.
Just watch the video.
You could just jump to like 50 minutes. Dalton's Law of Partial Pressures. Every particle exerts a force. So if I want to know the total force in a system, what would I do?
Add up the force of all the individual.
I'd add up the forces of all the individual particles. That's Dalton's Law of Partial Pressures. Really? That's it? And he got to attach his name to it? Yes. Yes, that is it. And he got to attach his name to that. That's a bit silly, but that's true. Okay? Said slightly differently, or in a more particular case, if we go through and take a sample of noble gases, and I take the partial pressure of each of those gases, and I put them all into one container, what is the total pressure of that sample?
If you took a sample of all the different noble gases?
I take a sample of helium, 125 millimeters mercury, neon at 45 millimeters mercury, argon at 158 millimeters mercury, and krypton at 17 millimeters mercury, and I put them all into the same container. What is the total pressure of that now container?
125 millimeters.
Not 125 millimeters.
That's not even pressure.
Just combine all of it.
You just add all the numbers up. Literally, that's it. You just add them all up. They're all the same unit. They're not the same substance. Okay? But the substance doesn't matter to us. Why does the substance not matter to us? Because we're looking at ideal gases. We're making big assumptions about the gases. Okay? So I don't want to go through the math of just adding, so I'm not going to do that. Absolute zero. One of the things that we end up generating out of the ideal gas law, okay, comes back to an absolute zero. Let's see how you guys do with this one. So PV equals nRT, okay, where T was our temperature. if we'd used degrees Celsius, or if we said, let's just stay in Kelvin, that we could actually go to negative Kelvins. I don't want to answer that question. What would be the problem if we could make it to negative Kelvins, if we could pass through 0?
If you can pass through below freezing?
It's not below freezing because it's Kelvin. What's the problem if I have a negative Kelvin?
You can't really.
It has nothing to do with standard temperature or pressure. I'm now outside of standard temperature. Pivnert is still valid.
Really, like, account for that.
Wouldn't it like make Kelvin useless pretty much? Because Kelvin's supposed to be all positives, they're supposed to be.
So there's a reason why we went to Kelvin, because it was all positive. Okay? Why do I have to stop at 0? Why is this now impossible for me to pass through? Officially, I can't even get to 0. I can get infinitely closer to 0, but I can't actually achieve 0 or lower. Why not?
Because the guy came up with it said so.
Okay, let's just make it 0.
Oh, if it's a
Let's make it 0, and let's solve for the number of moles in this system, right? So the moles would be equal PV over R times 0, right?
We're going to end up with 0.
Okay. If it was 0, I'd end up being dividing by 0, which, if you tried that in your calculator, it tends to scare the crap out of it. Right? It can't process that. It's physically not valid. Okay. If we tried to solve for, say, the pressure, that would say we had 0 pressure or 0 volume. Okay, 0 pressure might make sense with a vacuum, but 0 volume? We have something that exists but then has no existence. That sounds kind of... And this is where we have to be a little bit careful within that. You're right, within our assumptions. Okay, what if we passed through 0 and went negative?
You're going to have negative answers.
I'm going to have negative answers. Well, I have negative degrees Celsius. Why is that a problem for moles?
How do you have negative pressures, negative moles?
Can I have the volume? Not just the lack of something, but the now negative lack of something?
No.
I can't hold on to the I can't even use words to describe that. Same thing with pressure and volume. I can go to a 0 volume, but to have a negative volume, I'm now like imploding? Like it doesn't even make sense. A vacuum, again, doesn't have no volume, or the opposite of volume. Okay? Pressure, volume, and moles are all positive values. We can't pass through that. Can't. Okay? That's as big as I can do with air quotes with an iPad in my hand. Okay? And you might wonder, well, is that actually possible? Okay? For those of you who are like, chemists are horrible people, and this could go to Braxton because Braxton wants to be a physicist. Physicists have gone through and achieved negative Kelvins. Or achieved a system that would only be valid if we had negative Kelvins. We won't worry about it. Okay? So, limiting reactant concept. This is not a new concept to us because we've already talked about it. If we have 5 slices of cheese and 8 slices of bread, how many sandwiches can you make?
8 slices of bread and 5 pieces of cheese.
5 slices of cheese, 8 slices of bread. Why can I only make 4 sandwiches?
Because there's 8 slices and each divided
Because
by
we look at our equation, our chemical equation.
We just look at the chemical equation. So I look at the chemical equation. 5 slices of cheese. 1, I should get 5 sandwiches, yet you're telling me only 4. So you mean I have to look beyond just one reactant, I have to look at both reactants and see how they could possibly make sandwiches? Yes. I have to look at them as independent systems and then compare those systems to each other to find the smaller amount. Yes. Exactly right.
I would advise, however, against the
2 moles of sodium carbonate are mixed with 2 moles of water and 1 mole of carbon dioxide. How many moles of sodium hydrogen carbonate are produced? Right. 2, really?
Yes, on the equation.
2 moles of sodium carbonate. Does it really sound like that? What's a nice response? Sodium hydrogen carbonate, right?
Yeah.
So I want to get rid of the moles, sodium carbonate. What do I want? Moles, sodium hydrogen carbonate, right? Okay, where do I find that conversion factor?
In the equation.
Chemical equation. What is 2 times 2? 4. Didn't you just tell me the answer was only 2?
Well, I misheard you. You said 2 moles of sodium carbonate. So if it only takes 1 to make 2, then
So the answer is 4 now. Just like I could make 5 sandwiches. What do you mean no?
We're going to make 4 sandwiches.
Why could I only make 4 sandwiches? How did I determine that? I had to evaluate the other reactants. Am I given other reactants? What other reactants am I given? 2 moles of water. Set it up. Moles, H2O, moles, sodium hydrogen carbonate. What's the relationship?
1 to 2. 1 H2. Oh,
No, it's 2 to 1. I was wondering what was going on.
Sorry.
Which would give me
4.
4 moles. Oh, maybe you guys were still wrong because you guys still said 2.
I'm still saying it's 2.
You're still saying it's 2 because why?
Because we still have CO2.
1 mole of carbon dioxide.
1 mole of CO2 times. I want to get rid of the units of moles of CO2. What do I want?
2, 1, 2.
Moles sodium hydrogen carbonate. 2 over 1. This becomes
4. 2. Oh, 2.
2 moles of sodium hydrogen carbonate.
Send encouragement. I totally spaced on CO2 and got this wrong the first time, guys.
I would bet most people guessed and got lucky. Okay. We have to go through and now evaluate. Same deal as we went through the last time. Right? Just like with our sandwiches. What is the largest amount of sodium hydrogen carbonate I can make given this question?
2.
2. Isn't 4 bigger than 2?
Yes.
Yeah, but you can't because you need more than 1.
I would need more CO2. CO2 is now the limiting reactant. It prevents me from carrying the reaction forward.
that makes...
Okay? Why can this become more difficult?
Because you have to do every single one every time.
Every single one, every single time. Why is this question relatively easy in comparison to the ones we've already done?
Well, if you just simply
Because you're only dealing with 2 to 1.
I'm only doing a single conversion factor between moles. Do I go into the lab and measure moles? No. What do I go into the lab and measure? Grams, which means
you'd have to convert grams.
I would have to convert grams to moles.
Every single one.
And then I'd have to do moles to grams. The limiting reactant becomes more difficult because it's not just going through the chemical equation, it's going through your mole to gram calculations as well.
If you were able to find your limiting factor first, that might be.
If you knew your limiting factor first, that would make it easier, yes. Okay, but if they're all in grams, you have to go through this process. Okay? So you have to solve for every reactant. Okay. So we are, and it depends on the information given. Okay. We are out of time, but before you pack up, because we've got some useful information here, we have this concept of percent yields. We didn't talk about it, which means it will not be on this test. It will be on the final. It was in the reading, and I also don't think it's that big of a concept, but we've got enough stuff to worry about. Okay? Percent yield, this is a fun question to look at. To answer this, you have to do a limiting reagent calculation first. Most percent yield questions require that extra layer on top of them. Okay? Conversion factors, where to find them. We've got a list just of everything. We've already talked about this multiple times. This information needs to get purged onto the exam almost instantly so that you don't have to think about it later on in the exam. Get that constant information down so you don't have to think. Your conversion factors, remember measurement or number, measurement, and substance. The measurement and the substance are very important to watch out for. The measurement was important in the last unit. The substance is now important in this unit. Right? So you have to watch out to see if you're converting substances. Right? The last big thing, well, this says quiz, don't worry about this, is a massive, massive limiting reactant percent yield question that requires a whole bunch of steps to get answered first. Okay? That would be your process behind it. If you can solve this one beginning to end, you're ready for the test. Empirical formulas and molecular formulas. Come on. We did not achieve. We did not get there, which means those two concepts will also not be on the test. That said, to solve your empirical and molecular formulas, it is this slide, follow the directions.